Hello, everybody. Welcome back to the show, Science Dispatch Podcast. My name is Cameron English, your host as always, joined by the always faithful, dedicated, thoughtful Dr. Chuck Dinnerstein, Director of Medicine at the American Council on Science and Health. Chuck, what's going on?
It's a beautiful day in the neighborhood. The seasonal occupants have vanished, and we're only a few hours away before the apple and pumpkin pickers arrive to clog the highway.
It's beautiful. It's beautiful. I love the fall time. It does have some of its downsides, but the turning of the leaves is wonderful. I get to take my kids to the park and
the leaves change color in California. I don't remember that.
They do. It's very subtle. You know, you walk out one day and everything's golden brown. You go, wow, when did that happen? It was 113 yesterday.
So they don't really change so much as crisp.
That could be part of it. That definitely could be part of it. Although you're a Southern Cali boy, from what I remember. So you lived in an urban jungle where there probably weren't very many trees, would be my guess.
Well, the palm trees, they would go from a kind of a greenish to a tan for the season. That would be it.
I got you. Okay, very good. Well, I hope everyone is enjoying the start of fall as we are. It gets more pleasant as you get older, I think. But in any case, we've got another story from Chuck to discuss today. Chuck, I think these kind of stories are you at your best because you're breaking down stuff that can be really technical. It could fly right over people's heads if we didn't have folks like you to go, hold on. Here's the base of the pyramid. Here's what you need to know. And I think that's very helpful. So this story is called Silent Killer, How Fibrin Drives COVID-19's Hidden Damage and Long-Term Brain Fog. Of course, we're talking about the much ballyhooed long COVID in this story. To be honest, I haven't followed this very closely, Chuck. I mean, I've heard things ranging as far as it doesn't exist to it's the next apocalypse. It's turning people into zombies. And it seems here, if I'm understanding this story right, you've highlighted some research that appears, it's still pretty new, but it appears to have pinpointed at least one of the key pathways involved in long COVID. Is that basically correct?
I think you're correct. And you're right. I mean, long COVID is one of those diseases that's still in search of a diagnostic biomarker. So we don't really know. So it's fair to say that there are people that say that it doesn't exist, and there are people that say that it's 15 or 20% because we don't really have a good diagnostic criteria for who actually has long COVID. Though it's clear that there are people that develop long-term sequelae after COVID infections, and that's how it's been named. But it joins a host of other kind of vague autoimmune diseases, and they have begun to tease out within groups of people that are described as having long COVID various physiologic changes, or in this case, a very interesting biomarker and physiologic change at the cellular level. So in brief, if we all remember back to original COVID, one of the hallmarks of the disease was the increased amount of microclotting. And the clotting was rampant, and it was especially problematic in the lungs where little clots would form and ultimately would impair the ability of oxygen to get across the lung membranes and oxygenate people. And you remember all the stuff about the ventilators and all the discussion subsequent to that about who actually had needed the ventilators versus not. So clotting has always been a hallmark, I think, that everybody could agree that was pertinent for COVID. And these researchers did some studies, and I'm going to say right off that all of this stuff has been done in mice, and that mice are not little people, but it does give a very intriguing look into what may be part of the underlying mechanism. So they talk about fibrin, and fibrin is part of our clotting system. It's the meshwork that allows a clot to form. And if you think about the blood and the blood elements going through, fibrin, when it's transformed from fibrinogen, its soluble form into its insoluble form, forms like a chicken work network that begins to capture other parts of the clotting cascade to form a clot. And you can think of these fibrin deposits as little plugs. So if there's a small leak in a blood vessel, fibrin will form in that area, form a plug, stop the leak. It also has the same effect on the vasculature of the brain at the blood-brain barrier, so that it has some ability to penetrate across the blood-brain barrier. And the brain is immunologically separate from the rest of the body. So let me just say that. In any case, what they found is that the spike protein of COVID caused changes in fibrinogen so that it caused a far more dense fibrin mesh to form. And that fibrin mesh that formed was so dense that the enzymes that usually break it down, which we call fibrinolytic enzymes, took a lot longer to break them down. So these fibrin deposits last longer. And as it turns out, in addition to forming a scaffold for a clot, the fibrin is also able to send out some signals to the rest of the immune system that we're having a problem over here and bring us some help. And those inflammatory signals continue on after the fibrin is deposited, and because it's hanging around for a longer time, that inflammatory signal lasts longer. And all these things have been shown in various ways in their rat studies. And the other thing is that the fibrin suppresses what are called natural killer cells, which makes it possible for virus to hang around longer. So the end result is that it is the interaction of fibrin with the spike protein that causes a more prolonged inflammatory response and muted immunologic response to COVID than to other viral infections. And they believe that that's responsible for it because you do not need to have an active infection to have spike protein continuing to be circulating in your body. The spike protein by itself is not infectious unless you have an intact viral particle. It's no way to inject itself or to introduce itself into the cell. And I make the point that this is, for those with a more conspiratorial bent, the COVID vaccinations do not cause the mRNA to replicate to any large and uncontrolled degree. So this is just an abnormal sequelae to long COVID, that these people have the spike protein hanging around longer.
Now, they also appear to have figured out a way to mitigate this or maybe even reverse it. In mice, at least. Can you talk about that? It was giving the mice antibodies that seemed
right. They gave them monoclonal antibodies directed at the spike protein, and what they found was that by taking the spike protein out of the equation, they were able to mitigate this abnormal fibrinogen response. It's certainly more difficult and comes with more of a threat to the system to try and come up with antibodies against fibrin, because our vasculature is inherently leaking a little bit all the time. So taking away its first line defense and its stop leak is not a good idea. So they found, again, is using monoclonal antibodies targeted against the fibrin, that it reduced the inflammation and that it seemed to clear up a lot of the inflammatory response, especially what they decided was white matter damage in the rats that had been given long COVID. So that may very well be, it's certainly a tantalizing way to think about whether that may be responsible to some degree for the brain fog that people describe.
So I imagine studying this thoroughly in humans would be really difficult, but are there any existing studies that have looked at monoclonal antibodies that might suggest that this effect occurs in humans as well?
No, because I think all the studies so far have been really directed at the acute phase. of this. And I think that there are some, there is an NIH long-term study looking at long COVID, but I don't think that it's gotten to be this targeted. We're kind of in the phase of trying to figure out where are the most promising places to look for an understanding and a solution to the problem. So it wouldn't surprise me that over the next few months whether they'd have some targeted monoclonal antibodies and they identify a group of people with long COVID and give it a whirl. Now, whether it proves to be effective and to what degree it proves to be effective is going to still contend a lot on how they define who has long COVID. So there is kind of a chicken egg problem in getting to the bottom of this one.
Okay, so you're the vascular surgeon between the two of us. How well do you think this is gonna translate? And I mean, serious question though, because as you said, I imagine that the circulatory system of a rat is very different than ours.
Yes,
So.
but I think it has a lot of legs because I think it helps explain how it's possible that a real world event that we saw, these microclots forming, can go on to continue to cause long-term problems. So from my point of view, I think it has, I think it has legs. I think it's going to turn out to be part of the solution. I think that, with any number of diseases, that there's rarely one issue that tips you over from being clinically asymptomatic to clinically symptomatic. And that there very well may be more than one problem underlying this. Though what those problems ultimately are going to be, I don't have the infectious disease chops to say at this point what they would be. But you can see how people that are, for instance, immunocompromised already, and then you add this fibrin spike interaction that causes further immunocompromise, how that might push them over into having a longer term problem.
It's fascinating stuff, and we spend a lot of time mocking animal models on this podcast, or at least I do. But this seems like it was actually a reasonably designed study, even though it is in rodents. And they're not doing anything impractical, right? They're not like injecting the rats with tumor cells and going, well, they got cancer when we did that, So.
Oh, exactly. I think that this is a very down-to-earth, practical study. It has a clear clinical implication, and there are ways to go about testing it. So I think that it's a worthwhile avenue to pursue. So hopefully we'll see something a year or two down the line to talk about that. Again, it also points to to what I find so fascinating about our underlying physiology. It's not always where we look that the answers are to be found. I mean, I would not have anticipated that there was some type of interaction between a portion of the virus and and our coagulation system that would set off this very tremendous clotting cascade, and that it would work not by really altering the clotting response, but altering the timing of the clotting response. The problem, to a large degree, is it forms these very dense fibrin clots that take a lot longer to break up. So the autoimmune effect, the inflammatory effect, is there for a lot longer. So it's timing. It isn't necessarily the sequence or what's going on, but how long we stayed in one phase versus another.
So, and some of the keys are not always under the lamppost.
Exactly.
Sometimes they are somewhere in the dark, and we got to look there. Well, good stuff. We'll follow this. I'm sure there will be more on this because long COVID doesn't seem to go away, not in terms of just the condition itself, but everyone's always talking about it to some degree. So we will revisit this. In the meantime, follow us on Twitter. It's at ACSH.org. I'm at CamJ English. Chuck's there, but he is smart and he doesn't spend any time there. So just tweet at us, send us messages, and we'll get them to him. Go to our website, acsh.org, click the subscribe tab up top, punch in your email address. We will send you the articles we talk about on the show. As always, thank you for joining us, and we will see you next time.